in the next several videos, we're going to revisit space-time diagrams. In particular, we want to extend them to the cases involving the special theory of relativity. And we're doing this because we'll find it's particularly useful next week in week 7 when we talk about some of the paradoxes, such as the twin paradox and the pole in the barn paradox. So first here, we just want to remind ourselves of a couple things about space-time diagrams, and then we're going to look at it also in the case of a light beam, how we actually plot that on a space-time diagram. So remember, we've got, in our basic configuration, we've got the x-axis horizontally, the t-axis vertically, and we can plot the path of an object through space and time on the diagram. So this line right here, we can see at t equals 1, we'll just assume it's 1, 2, 3, 4, and x2, 1, 2, 3, 4, negative 1, negative 2, negative 3, and so on and so forth. So at t equals 0, x equals 0, this object is at the origin, basically. And then 1 second later, it's here. It's moved 2 positions to the right along the x-axis. And then at 2 seconds, it's 4 positions to the right, and so on and so forth. And remember, all our cases here, we're just going to be doing constant velocity motion. That, remember, if you get a curved line, that means the velocity is changing, and you have accelerations involved. So this is the space-time diagram, or remember, the world line is what we call it, the world line of an object moving in the positive x direction through time, t equals 1, t equals 2, t equals 3, and so on and so forth. This is the world line of an object moving with actually a little bit slower here, because if you think about it, this object here moves in 1 second, it moves over 2, x equals 2, and then in 1 second this one moves, well, roughly, approximately 1/2 there, perhaps. And so its velocity is going to be slower. In fact, as you've already probably read here, I've got a reminder that velocity is the change in distance, the displacement, divided by the elapsed time, delta x over delta t, or we also call it the run over the rise. The run is the elapsed distance covered in the x direction. The rise is how far up on our diagram you go in time. And that also is 1 over the slope, because remember, the slope of a line, by definition, is the rise over the run. It's the vertical distance covered divided by delta, well, whatever, in this case it's x here, the horizontal distance covered. So that if you have a line that's a low slope, so it's not sloping very much, that means a high velocity. It's covering a lot of x in a short amount of time. A line of this slope, a higher slope, means that it's covering shorter distances in a given amount of time. And so this is a high velocity here, this is a lower velocity. Also note, of course, that we can have things going backwards. We can have things going in the negative x direction, so that's what this line here represents. Okay, so that's just a quick reminder of some of the basics of space-time diagrams. We'll come back to this in a minute or two. Let's move over to this diagram, though, and talk about lines of same location and lines of same time, or the latter one here is sometimes called lines of simultaneity. Lines of simultaneity. And essentially what we have for lines of same location, that means x equals a constant. In other words, and I've drawn in green here several of them, this is the x equals 1 line. And remember what that means. If this is the world line of an object in space and time, it means it's just sitting there at the x equals 1 position. As time goes on, it's always at the x equals 1 position. This one's always at the x equals 2 position. So this is the line of same location for x equals 2. This is the line of same location for x equals 3. And similarly for negative x equals negative 1, x equals negative 2. So again, if this one here was the world line of an object, it would mean it's sitting at x equals negative 2, motionless in this frame of reference, of course, and so on and so forth for each of those. So those are lines of same location. Lines of same time, or more commonly we say lines of simultaneity, that's where t is a constant. And so here we have, the t equals 1 line. This is the line. Everything that happens at t equals 1, any place on any x here is on this line, the line of simultaneity. So if I have something that occurs, right here, and also something maybe that occurs over there, those two events are simultaneous in this frame of reference because they both occur at t equals 1. And here's the t equals 2 line of simultaneity, t equals 3. And of course, you can have any line in between those as well. So in our diagrams, horizontal lines here are lines of simultaneity. Anything on that horizontal line, any event on that horizontal line means it happened at the same time. They were simultaneous with each other. Of course, that's why we call it lines of simultaneity. And that's where t equals constant. And of course, the x-axis itself is t equals 0. So it is a line of simultaneity. And I forgot to mention the t-axis, the vertical axis, is the x equals 0. So if you have something sitting at the origin in our frame of reference and not moving at all, as time goes on, its world line would just be a vertical line right along the t-axis there. Okay, so lines of same location, lines of simultaneity. Let's also do a couple other things on here, remind ourselves of one more thing here, that we can have things change direction, of course. And so something like this, if it's a world line going out this way, and then maybe back that way. Okay, so this is an object. Think about this a minute. What's going on here? Remember, these space-time diagrams are not the actual physical situation, right? They're the representation of what's going on. Everything is going on along the x-axis here. So this is not an object shooting up at some angle and then at another angle in another direction. It's just moving along the x-axis. So this line here says, during the first 2 seconds, 1, 2 here, it's moving over here to about this point. So it's moving along the x-axis to there. And then it changes direction. It stops and changes direction and starts moving back this way at, actually, remember, a little faster velocity here, because lines of lower slope mean a faster velocity. And then at this point, maybe it stays right there. So now it's stopped for the next few seconds, and then maybe goes off that way again. So this is an object that moves here to the x, over here, x equals maybe 2.3 or something, and then moves back at a faster velocity over here, and then stops there for a few seconds, and then starts moving to the right again at a certain velocity given by the slope of that line. Again, lower slopes mean higher velocity. So this slope here is closer to the horizontal, so it's a higher velocity than this slope or that slope. So just from looking at the diagram, you can get a sense of what that object is doing. And again, this is only along the x-axis here. That's what the diagram is showing us. And the vertical axis is what's happening throughout time. So that is just a reminder of some of the basics of space-time diagrams. Pretty much everything, not everything we covered before, but some of the main points we've covered before. I actually don't remember if we introduced these concepts or not, but pretty basic here. We didn't really need them until now. We're going to use those in the next couple of video clips. So we do a few things. But one other thing we want to look at here is, what if you shine a light beam? Say you have a flashlight at the origin here, and you shine that light beam along the x-axis. So again, I'm just going to shoot it that direction, laser beam or whatever. How would we plot it on the space-time diagram? What would its world line look like? Well, clearly it has a velocity c, and now we have to think about units a little bit, because often, at least previously, we had maybe units x equals meters, time equals seconds. So let's just think about that. If x here was in meters and time was in seconds, what would the world line of that laser beam going off in that direction, what would that look like? Well, we know it travels 300 million meters per second, or 300,000 kilometers per second. So if this is 1 second here, its location along the x-axis at that point would be 300 million. Clearly, I'm going to have a problem fitting that on my whiteboard here, right? It's going to be way out there. Roughly, I'm just guessing, probably 3 million meters that way, at least, maybe even more than that. So it'd be a long ways away. And so we have a line. If we actually had to plot it on here, it wouldn't even look like something like that. You wouldn't be able to plot it very well using these units for time and space, the x distance. So what we typically do is we adjust the units. We'll get rid of that in a minute. And so instead of meters, we might say, well, we could do kilometers, but then it's 300,000 kilometers per second. So again, way out there. So what we might have to do instead here is if we've got units here, we might say this is 100,000 kilometers, this is 200,000 kilometers, this is 300,000 kilometers. Okay, we'll do that. So just imagine that's there. So then in 1 second, the light beam would travel 300,000 kilometers, and this is where it would be, right there. And then in another second, it would travel another 300,000. 1, 2, 3, so it would be out here someplace, roughly speaking. Just very roughly there. And so, that'd be the world line of our light beam, assuming x then is 100,000 kilometers, 200,000, 300,000, 400,000, and so on and so forth. Now that works, but it's a little awkward, to have these huge units on the x-axis. You could certainly, another way you could do it, let's do it like this. Okay, so that's one option. Another option, let's say we like x in meters. It's fairly intuitive. We have a sense of how long 1 meter is, or 1 yard roughly, 3 feet, if you want to think about it in those terms. So what if we want to keep meters here? How could we change our time? Well, we could, instead of seconds, we could do nanoseconds. So we have nanoseconds. Billionths of a second, using billionth in the American usage there. So nanoseconds. And therefore, you may remember that in 1 nanosecond, light travels approximately 1 foot, approximately 1/3 of a meter. So in 1 second here, the light beam would be 1/3 of a meter, so it would be roughly right there. And then in 2 seconds here, it would be, actually this would go up to 3 seconds, because in 3 seconds roughly it would travel to a meter at that point, and so our line would look something like that. So you can see we get different drawings here just depending on how we change the units, of course. So this is meters and nanoseconds. That also is not too convenient. We don't typically think in terms of nanoseconds, especially in maybe if you're doing tabletop experiments in a laboratory, but often we're thinking about astronomical distances. And so we think about this a minute and we say, oh, remember what we were talking about last week, and that is that useful units for the speed of light are something like light years per year, or light seconds per second, because then c just becomes 1. So it's 1 light years per year. Because by definition, of course, a light year is the distance light travels in 1 year. Or light seconds per second, or light days per day, or light months per month, or whatever unit you want to use there. Just remember, light years is a unit of distance, not a unit of time. So what if we did something like that? Because then, as we will see, our diagram becomes very nice. So let's just say x is in light years. And then whatever we choose for x, that determines our time unit here. It doesn't have to technically. We should put seconds there if we wanted to, but it doesn't make much sense diagrammatically to do it that way. So light years and years, c is 1 light year per year. So that means in 1 year, it goes 1 light year. So if we're putting the speed of light, our laser beam shooting off here, in 1 year, it's gone 1 light year. In 2 years here, it's gone 2 light years, and so on and so forth. 3 years, 3 light years. And so we get a nice line at 45 degrees. Nice symmetry to that. And therefore, this is what we're going to choose for our space-time diagrams when we're using them with the special theory of relativity. We're going to have light years per year typically, or it could be, again, light seconds if we want to do seconds for time, and so on and so forth with that. Another way sometimes you will see this, by the way, if you read other books on the special theory of relativity, and a little later on in the course I will give you a list of some nice books that for those of you who want to go beyond the course, sort of next steps you might take for books out there. Sometimes you'll see this as CT on the vertical axis there. Okay, we won't put that in. We're just assuming that c is in light years per year or light seconds per second, and so on and so forth. But if you see that, that essentially is the same thing we've got going on here. Because if it's c is 300 million meters per second and time is in seconds, c is essentially in 300 million, you put meters, x in the same units as well, and you essentially get the same idea here. So, just a reminder, we're going to take c as 1 light years per year typically, and that means the slope of our beam of light remember, it's along the x-axis. It's not traveling at some angle here. It's just going along the x-axis at an angle of 45 degrees. So that's actually a slope of 1 because it's just, if we've got rise over run, the rise here is 1, the run is 1. Or the rise, if you go over here, it's 2 here. Rise is 2, run is 2, and so on and so forth. And that means the velocity is 1 as well. It's 1 over the slope. In other words, the velocity is 1 light year per year. Okay, so that's a brief review of space-time diagrams, and then also how we're going to put something going the speed of light. So this is the world line of that light beam going along the x-axis here. And then we're going to expand on this in the next couple of video clips and see what happens when we introduce some of the relativistic concepts into this.